Hello and welcome. In this video we are going to talk about orthogonal projections. So one common objective in working with a basis of vectors that span some subspace in Rn is to find vectors that are orthogonal to one another. Recall that span and subspace put together mean in layman's terms where can we get to with the vectors that we have within Rn by putting scaled vectors together tip to tail. So one of the first things is that we should recall here is that a basis basically means that it is a set of vectors that span some space. So for instance, the 1, 0 vector is a basis, but it's only the basis for anything that falls along the positive or negative x-axis. So we can scale it up, we can scale it down, we can multiply it by a negative scalar and have it point over here towards the left. So that is a basis, but it's not a basis for all of R2. We could say this is a basis for the line where y equals 0. So basically that is, if you look at the rise to run ratio, any line that lies along the horizontal axis is the line y equals 0. So it's a basis for that. Now when we put together two vectors that form a basis for, or two vectors like the 1, 0 vector and the 0, 1 vector. So here we have the 0, 1 vector, and then over here we'll have the 1, 0 vector. So these actually form a basis for all of R2. Form basis for R2. So all we mean by that is that we can get to anywhere we want by putting these two vectors together tip to tail. So the important thing is just here to recall that in this case, y equals 0, this is a subspace of R2. So it's really just a line, but that is a portion, sub by within. It is within the space of R2, but doesn't allow us by itself to get anywhere we want. So why do we want orthogonal vectors? Well, as we've seen from our previous lesson, you can really quickly compute coefficients to find what are the scalars for a bunch of vectors to put together tip to tail to produce another vector. They have the nice features that any two orthogonal vectors have a dot product of 0, which makes things very convenient mathematically. Additionally, we will see how much simpler matrix algebra is with these features. We first begin with a simpler case that will help us generalize the mathematics. First off, if any two vectors span some space, say a plane, then it is possible to rotate one of the two vectors such that both vectors are still on the same plane, and those vectors are now perpendicular. But how to do this is not quite yet evident. So let me draw a picture of what I'm talking about here. If we think about this as being some sort of plane, and on this plane we have two vectors. So maybe one of them points here, and the other one points somewhere else along that. So using these two vectors tip to tail, because this is a two-dimensional subspace, I can scale one of them up and then put them together tip to tail to get to any point I want along that plane. Let me move these up a little bit here. So with these two, I can get anywhere I want on this plane. But imagine that we were able to rotate this vector such that it still lies within the plane, but that it suddenly becomes perpendicular. So we can actually rotate one of these guys, and now we use this vector right here, and we use this vector right here as our basis for that plane. So there's something called the Gram-Schmidt orthogonalization process that will help us do this later on, but we're not quite at that point yet. Now, projections onto planes and projections of vectors onto lines are really valuable when you think about regression analysis, finding linear regression equations, quadratic regression equations. Those are things used a lot in mathematics and the sciences, and data science. Suppose that we have a vector y in 2 dimensions. So here it is. We can split this vector up into two vectors such that when we add these vectors together, we arrive exactly at the tip of y. However, let's choose these two vectors to be perpendicular to one another. That is, right, y is going to equal the sum of some vector called y hat plus some other vector called z. Okay, so what we've got going on here is that we have this vector right over here, this guy that runs, that's going to be a component of the y vector, and we're going to call that y hat. And then we're going to have this second vector that's going to point from the tip of y hat up to the tip of y. And so now what we'll be able to do is we'll be able to say, well, you know what, if this vector here is the y vector, and notice that it's bolded, so it's omitting the hat notation, but here it's not bolded, so I have to put the arrow notation on there. So what I see here is that if I think about, and here's the representation of z. Z is actually this guy here. So there's z, this red vector is y hat, this black vector here is y. So what we know from adding tip to tail is that y, we can get to that point by adding together the y hat and the z vector, which is precisely what this is saying right here. Now again, it's not very useful to have vectors written in terms of other ones, or to have an extra vector name when I can express it in terms of the other ones. So we can see here that if I subtract y hat from both sides, I get y vector minus y hat vector is equal to z. And that's exactly what I'm saying here. Suppose we want to project the tip of y down onto some other vector, call it u. And suppose we are given both y and u. So imagine that we have this y vector here and we have this u vector over here. And what we want to do is we want to cast kind of like a sun would cast a shadow. Let's see if I can find and kind of represent the sun. So here is going to be the sun. Okay, and the sun, if we put it right above here, and its rays would cast a shadow of y down on top of the vector u. So the shadow would basically end right there, and the red vector represents the shadow that we would see from the vector y above here. So the thing is, in order to find out y hat, we don't often know that u is just some vector that could be really long or really short, but the y vector projects down upon it. We want to know where is it going to cast its shadow. So in order to be able to solve this mathematically, we first are going to describe some terminology. First of all, we see that y hat is the orthogonal projection of y onto u. So there's y. Y hat, which is this red vector, is the projection of y onto this vector called u. And we write that as y hat equals the projection of y onto u. We see that y hat, that vector, lies on the same line as u does. And so if I'm given u and I'm not given y hat, then all I can say is that y hat is a constant multiple of u. They're on the same line, and if two vectors are on the same line, they're scale multiples of each other. Okay, this means that y is some multiple, say, by a factor of alpha of u. In order to find z and y hat, we need to solve for alpha. What can we infer from the picture we have drawn? Are there any helpful facts that might help us? Well, we've already described orthogonality as giving us the ability to have zero dot products. So I see that, first of all, y hat and z are perpendicular. So I can make a couple of observations. One, y hat and z are perpendicular. And I can actually write that like this. Y hat is perpendicular to z. And I can also observe that u is perpendicular to z. U is perpendicular to z, because remember, y and u lie along the same line. So I'm going to need to try to come up with an equation of some sort to find and solve for alpha. Well, I'm going to go ahead and use the fact that u and z are perpendicular here. And what that means is that if I take the dot product of u dotted with z, I will get 0. Okay, so I'm going to get 0 because they're orthogonal, so they'll have a 0 dot product. Now, z is equal to, so far it's not evident how we're going to solve for alpha here, but if I write z in terms of what it equals, it's the difference between our y vector and our projection vector. Again, that equals 0 still. And now I also know that y hat can be expressed in terms of u. And the reason I want to do this is because y hat is an unknown, and I want to express it in terms of something that is known. This is one of the common objectives in mathematics, is taking something new and expressing it in terms of old things. So here we're just solving for alpha. That's just going to be the factor by which we need to scale the u vector to produce the y hat vector. All right, so next we want to distribute that out. Well, before we do that, we said we're going to make a substitution. So y hat is some multiple of u. And already I can see that now I have an equation that involves things I know and only one thing that I don't know that I want to solve for, which is alpha. So if I distribute, I'll have u dotted with y minus alpha times u dotted with u equals 0. And now I can isolate alpha. Remember, a dot product is a scalar, so those are, as long as we move those together, u dot u is just a number. So this just represents a scalar, and this just represents a scalar. So if I rearrange things, I'll see that alpha times u dotted with u equals u dotted with y. And now I can solve for alpha. Alpha equals u dotted with y divided by u dotted with u. So we just solved for alpha in terms of the things that we were given in the problem. If we want to find y hat, though, y hat is going to be that alpha value that we just found times u. So to find y hat and to come up with a formula for y hat, in terms of what we know, we should now make the observation that y hat equals alpha times u. There's alpha right there. So now I can put those pieces together and say y hat equals u dotted with y, that should have a vector hat over it, dotted with y over u dotted with u. That's just alpha. And this right here, by the way, is a scalar because you have a scalar divided by a scalar. And then that's going to scale the u vector. And there is our formula for what we're calling y hat. Again, y hat is just the projection vector of y onto the line u. Now there's lots of reasons why we would do this. This also leads to the Gram-Schmidt process, which helps us do precisely what we wanted to do up here, which is to take two vectors that span a space and rotate one of them in order to make the two vectors perpendicular. So let's go ahead and just do a quick numerical example. Let's go ahead and find the orthogonal projection of the vector 3, 5 onto 7, 1. So the first thing I'm going to do is just sketch this out. 3, 5, 1, 2, 3, 4, 5, 6, 7, and this will go up to 5. Okay, so 3, 5 is one of the vectors. That's this guy here. 7, 1 is this vector over here. Well, close enough. You get the idea. And what we want to do is we want to find the projection of this vector so that that vector right there is going to be perpendicular to my vector u. And remember, the vector that we actually want is this vector here that stems along u but stops where that shadow is cast down. Again, now imagine our sun is kind of up here and it's casting a shadow perpendicular to this surface. So to find that vector, we already know how to do it now. This vector is the y hat vector. So to get y hat, all I have to do now is just take u dotted with y. So, wait a minute, what's u and what's y? We got to identify that first. Y is the vector that we're trying to project down onto u. So that's an important distinction even when the vectors are not called by name, y and u. So u is the vector 7, 1. And that's going to be dotted with 3, 5, divided by u dotted with u. So that's 7, 1 dotted with 7, 1. And then we're gonna, that's our scalar multiplier right there. Now we need to multiply that scalar by the vector 7, 1. So let's take care of that dot product. We're gonna have 7 times 3 is 21, plus 5 is 26. This will be 49 plus 1 is 50. So 26/50ths of the 7, 1 vector. So basically we have to cut that u vector basically in half to be able to have that new vector land as the projection of the shadow of the vector y. And we can multiply this all out and stuff. I think 26/5 is 13/25 if you want to leave it like that, and then multiply it by the 7, 1 vector. But that's adequate for now. Now, we also have common applications for this. So, like, for example, suppose you have a wind speed that has a vector of y equals 10, 12, where 10 miles per hour is the wind speed due east, and 12 miles per hour is the wind speed due north. So collectively, this vector says the wind is blowing in the direction of 10, 12. We want to know how much tailwind an airplane encounters that is traveling along the displacement vector u equals 25. So if we draw a picture of this to more clearly analyze what it is that we're after, the vector 10, 12 is going to be some vector that's going to be, it's going to be somewhere in the first quadrant, 10 units over, 12 units high. Whoops, nope, not what we wanted. There we go. Okay. So 10, 12 will be somewhere right about there, let's say, and then 25 will be a lot lower, and we'll point actually somewhere right about there. So we'll say that's the vector 25, and this is the vector 10, 12. Now, some portion of this wind is really, regardless of where you're standing, you're going to feel some of that wind hitting you. Whether it hits you from in the front or hits you in the back, you're going to feel some of that wind. So it's fair to say that some of that wind vector will be in the direction of this 25 vector. So this is precisely what we want, is to project this down onto here and think about taking this 10, 12 vector and breaking it up into two components, one which is parallel or in the direction of the plane, and one that is perpendicular to the plane. So there is, in fact, some wind that is going directly upwards, and there is some that is going directly against the tail of the plane. So this is my y vector. This is the one that I'm trying to project. This is my u vector that I'm trying to project down onto, and this y hat vector will be my wind speed in the direction of the plane. So once again, we'll take y hat is equal to u dotted with y, so 25 dotted with 10, 12. And you do not want to mix up u and y. Always ask yourself, which vector am I projecting and which vector am I projecting onto? And that will immediately tell you what is y and what is u. And down here we have 20 and 5 and 20 and 5 multiplied by the u vector, which is in the direction of the airplane, which is 25. So let's see, what do we get here? We get 200 plus 60 is 260 divided by 400 plus 25 is 425 multiplied by the 25 vector. Now, we want to know how much tailwind an airplane encounters. So this is the tailwind vector. This is the tailwind vector, but we want to know the magnitude of that tailwind vector. So let's go ahead and multiply this out real quickly. So here's the components that we get, and notice that overall, if we find the length of this, that should be smaller than the actual wind speed, because the wind is going to be going at the fastest rate in the direction that it's pointing. So the amount of wind, the wind speed in this direction should be lower than the wind speed in the direction that it's going. So to find the magnitude, to find the wind speed, remember these are all in miles per hour. So when we square and square root miles per hour, we're still in miles per hour. And we get 12.6 miles per hour in the direction, or we could just say tailwind. And if we found the magnitude of the actual wind speed in the direction it's going, I kind of mentioned that y hat, the magnitude, is going to be smaller. The magnitude of y will be the square root of 100 plus 144, which is 244, and the square root of 244 is 15.6 miles per hour, and that's the actual wind. But the tailwind against the plane is a little bit smaller. This is the answer that we were after, but this allowed us to see that the wind itself is stronger. Now, another feature of, we mentioned orthonormal vectors, which are just vectors that are orthogonal to one another and that have been scaled to have length 1. So if we have an orthogonal set of vectors and then we multiply them or divide them by their magnitude, we'll be able to get orthonormal. Normal refers to of unit length. Suppose we had a matrix of orthonormal columns, u equals u1 up to un. This matrix is very nice to work with, but why? What happens when we multiply u transpose times u? Well, let's go ahead and take a look at a quick example. Let's say that I had the vectors 1, -1, and 1, 1, and that was my matrix u. Okay, well, these are orthogonal because if I take 1, -1 dotted with 1, 1, I get 1 minus 1, which is 0. So these two vectors are orthogonal. Now, u transpose is just going to be take the columns and turn them into rows, which will give us 1, -1 as the first row, and then 1, 1 as the second row. Now, when I multiply these together, look what happens. I'll take u transpose, multiply it by u. U transpose is the matrix 1, -1, 1, 1, and u is 1, 1, -1, 1. So when I multiply these together, I will get, well, first of all, I'll take 1 and -1, scale the columns, so 1 times the 1, 1 vector, minus 1 times the -1, 1 vector. Now I'll proceed on to the next two values, 1 and 1. We'll scale the 1, 1 vector plus 1 times the -1, 1 vector. And so these are orthogonal, but they are not orthonormal. But let's see what happens with respect to these guys. If we multiplied this out, here we get 1 plus 1 is 2, and here we get 1 minus 1 is 0, and here we get 1 minus 1 is 0, and here we get 1 plus 1 is 2. Interesting. So it's almost like we got the identity matrix. And the reason we didn't quite get the identity matrix is because these were not orthonormal. So had we divided all of these by the square root of 2, so let's say that these are not orthonormal, but they are orthogonal. So to make them orthogonal, if I divided both of them by their lengths, which the length of each of these vectors is the square root of 2, so if I took 1 over root 2 and 1 over root 2 and -1 over root 2 and 1 over root 2 here, and multiplied that by the transpose, so in this case we would be multiplying u transpose, the transpose of this, which would be 1 over square root 2 times, or -1 over square root 2, 1 over square root 2, 1 over square root 2. So this is the transpose of this guy over here, multiplied by u, which is 1 over square root 2, 1 over square root 2, 1 over square root 2 with a negative, and 1 over square root 2. And lo and behold, when you multiply these out, you're going to get the identity matrix. So as long as you have an orthonormal matrix, one cool feature of that is the transpose of an orthonormal matrix is actually the inverse of that orthonormal matrix. So we'll make that observation here. We'll say, since u transpose multiplied by u equals I, and you could also verify that and u times u transpose equals I, because of that fact, we could say it is the case that U transpose is the inverse of U. And this is our conclusion here. So that's just another feature, another useful thing about orthonormal matrices that makes life, you can imagine that this can make life a lot easier if you're working with orthonormal vectors. Now, I don't think we'll go ahead and discuss these here, but at least not all of them. Let U be an m by n matrix with orthonormal columns, and let x and y be in Rn. Then the magnitude of U times the vector x is just equal to the magnitude of x. Maybe let's go ahead and support this a little bit, at least see how the algebra works out. It's pretty cool. So the magnitude of a vector, we developed from last discussion that basically one way to do it is to take the square root of the vector dotted with itself. So in this case, it would be U times x transpose dotted with U times x. Now, when we take the transpose, one of the properties of transposes is that the transpose of a product is the product of the transposed components in reverse. And so what we have under the square root now is, you can see here we have U transpose U, which is I, and then because that's going to be the identity matrix, this simply becomes the square root of x transpose times x. And hey, this is just going to give us the sum of the squared components of x, which is the magnitude of x. And so that proves bullet point number 1. Similar process can hold here whenever you dot these two vectors together. Remember, this is really we should be putting a transpose for letter B. So the more grammatically correct way to write this would be if I dotted U x transpose with U y, then again I could apply the transpose operator and make this x transpose times U times U transpose times U times Y, and again that becomes the identity, and so this becomes x transpose Y, which, just by convention we just can say x dot y to make our lives a little bit easier. So these are really cool features, and this all stems from the fact that U transpose U is the identity matrix. So we looked at two-dimensional projections. Let's now think about orthogonal projections in general. This could be in any size dimensional space. We now know how to find the projection of a vector onto another vector. The importance of this is that when you project y onto U, you actually minimize the distance to the tip of y from the vector U, since right angles are capable of minimizing distances. So one thing that we know from trigonometry, and we won't really get into it here, but if you want to know the shortest distance between this point and this line down here, it's always going to be the distance that will, it'll always be the distance such that the line that connects this point to the line is perpendicular to the line we're projecting down upon. So this is going to be a useful factor. This allows us to minimize distance. So now imagine that we have some plane. So this could be a hyperplane in 20 dimensions, which we can't really visualize. But let's just say in 3 dimensions, W is some plane. That means it can be, there are 2 vectors that we would need to span this plane. So we have this vector y, which is this vector here, and we want to cast the shadow of y down onto W, and we're going to call that resulting vector that we get, the shadow vector, we're going to call that y hat. So once again, we have the sun up here, and it's casting a shadow down, and we're going to call that vector that's formed, we're going to call that y hat. As long as we are dealing with an orthogonal basis for Rn, then it follows that every vector is perpendicular to every other vector in this set. That's the definition of orthogonal. All the vectors are perpendicular to one another. It also follows that any sum of two orthogonal vectors is orthogonal to any linear combination of the remaining orthogonal vectors. So let's just give as an example here, for this to make a little bit more sense. If I take three orthogonal vectors, we'll call them u1, u2, and u3, and these are all orthogonal to one another, then imagine what happens if I form a new vector out of two of them. Let's just call this let's call this vector v, and we'll say v is equal to 2 times u1 plus 3 times u2. And we want to know, is u3 perpendicular to v? So let's take the dot product between them. If the dot product equals 0, then we know that yes, that is true. So let's form the product u3 dot v. Okay, well, v is, we could expand that as 2u1 plus 3u2, and now we can distribute this, and so we'll have 2u3 dotted with u1 plus 3u3 dotted with u2. Now, since u3 is perpendicular to u1, this dot product will be 0, and since u3 is perpendicular to u2, this dot product will be 0, and so the dot product between any linear combination of orthogonal vectors and another orthogonal vector, those two vectors are still orthogonal to one another. As a somewhat intuitive geometric example, consider the vector, consider this vector that lies along the z-axis, and then consider two vectors that are perpendicular to it, which are these two green vectors. Now, if I form a new vector out of these two green vectors, that vector is just going to lie somewhere within this xy plane right here. So maybe that new vector lies here. Well, wait a minute, isn't the red vector still perpendicular to that new green vector? Well, absolutely it is, because any vector that lies on the floor is going to be perpendicular to a vector that rises straight up. So that's also kind of the geometric intuition behind why this is true. So suppose we have a basis of three vectors spanning R3. So we can write, because we know it's a basis, they're orthogonal, that means they're linearly independent, that some new vector inside of R3 could be written as a linear combination of those three vectors. Now we can further break this down into just say, let's call, without loss of generality, let's call these two vectors added together, let's call that z1, because that's a brand new vector. And we'll call c3 times u3, we'll call that z2. That's, again, just a new vector. And we're adding those two vectors together to form y. Well, since u1 and u2 and u3 are perpendicular to one another, and we just showed up here that any linear combination of orthogonal vectors is still orthogonal to another vector that's orthogonal to both of those, we know that z1 and z2 are perpendicular. Because of this relationship, it follows that our vector y can be written as, well, wait a minute, we just said z1 and z2 are perpendicular. So if u1 and u2, so let me write this, u1 and u2 span W, that is, this sheet of paper that we have here, this plane, can be spanned by these two vectors, then y hat is a vector that's inside of that plane. It's just a linear combination of u1 and u2. And that means since z is perpendicular to it, that means the z vector is perpendicular to the plane itself. So all I really have to do in order to find out what y hat is find the correct linear combination of them to be able to reconcile the y vector. So once again, in our case, w is the span of the vectors u1 and u2. That is, the plane is what we can travel along with u1 and u2. So in effect, what we have just found is a way to break up a vector into its orthogonal components such that one of them, y hat, represents the orthogonal projection of y onto w, and z represents the vector connecting y to y hat such that it is orthogonal to w. So this is a really beautiful result. It's the generalization of what we did earlier. Same kind of idea, it's just now we're working with higher dimensional vectors. So suppose we wish to find a projection of the vector y, which is this vector 1, 1, 3 in this picture. You know, it's a little bit blurry, so y is the vector 1, 1, 3. On the plane formed by 1, 0, 0, which is this vector here, and 0, 1, 1, which is this black vector here. And those two vectors lie along the blue plane. Now we want to take that y vector and find the y hat, its shadow, as if we were to take the sun and kind of cast its rays straight down, we would want to know what would be the vector representing that shadow. So we've already said that y hat, we're in 3 dimensions here, is some linear combination of u1 and u2. And then plus c3, u3. But we're not given we're not giving a vector that's perpendicular to these two. And that's perfectly okay that we don't know a vector that's perpendicular to u1 and u2, but notice that these two vectors are perpendicular to one another because their dot product will be 0. And visually you can kind of see that as well. That 0, 1, 1 lies in the zy plane, and 1, 0, 0 lies on the x-axis. So we don't know u3, but that's okay because we're going to use something from our last lesson to be able to find out y hat. So we've already said that the two vectors that are inside the plane, the linear combination here, this is my y hat, and this right here is the z vector because that's going to be perpendicular to the vector that's inside the plane. So to find y hat, all I have to do is compute c1 times u1 plus c2 times u2. And to find c1 and u1, I have really two unknowns in here. I don't know what the y hat vector is, and I don't know what c1 and c2 are. So excuse me, we have 3 unknowns. But what we know from last time, if you have an orthogonal set of vectors, then ci, the ith coefficient, can be found by taking the vector itself, which in this case is called y hat, dotted with ui vector, divided by ui dotted with ui. It seems like this formula seems to pop up quite a bit. In fact, it popped up as the value of alpha in our previous example, and that is not coincidental at all. So to calculate c1 and c2, we don't even need to know u3 because this function only depends on the current vector u that we're finding the coefficient for and the y hat vector. I'm sorry, not the y hat vector, the y vector. So here I shouldn't have said y hat, I should have said the y vector right here. And the reason is because this is not the equation that we're working with. We're actually working with this one up here, where c1, u1 plus c2, u2 plus c3, u3 give me the y vector. We're just not going to try to solve for c3 because we don't have a third perpendicular vector. So to calculate this, we just need to plug in the parts. So we know that the y vector is 1, 1, 3. We know that u1 is 1, 0, 0. And then this is 1, 0, 0 times 1, 0, 0, which will give me a coefficient of actually 1 over 1. And so c1 is equal to 1. So this should be for c1, excuse me. Now, to get c2, we're going to do the same thing, but we're going to do y dotted with u2 over u2 dotted with u2. And in order to get c2, we're going to go through the same process. c2 equals our y vector, 1, 1, 3, dotted with our u vector, u2, which is 0, 1, 1, divided by 0, 1, 1, dotted with 0, 1, 1. And that's going to give me, I'll have 4 in the numerator, 2 in the denominator, and so C2 is equal to 2. So how can we be sure that this process actually works? Well, first of all, we've at least logically established it up here, but let's go ahead and now calculate the y hat vector. So y hat is going to be C1 times U1 plus C2 times U2. And C1 is 1, so we're going to take 1 times the 1, 0, 0 vector plus 2 times the 0, 1, 1 vector, and that's going to give me 1, 2, 2. So the y hat vector is the 1, 2, 2 vector, and the way we could check that this at least worked out is to confirm that it is perpendicular to the z vector. So in our picture, we could label this vector here, the y hat that we just found, as the vector 1, 2, 2. That's the red vector that we just located. We could get z as well. Z is just this, the actual, that's the projection, or that's the vector that represents the projection down onto the plane. And we know that that vector is y minus y hat. And that is because if you take y hat plus z, you get y, and so we could solve for z in that case. If I actually, so what I basically just found is the vector that if you project a line down, you get the minimal distance between the y vector and the y hat vector. So if I want to know, for example, how long is that, what is the length of it, how far is y from y hat? What I want to find is the magnitude of z, which we did this in the previous lesson actually. We want to find the distance between y and y hat. And so from above, we were told that y was the vector 1, 1, 3. So we could do the magnitude of 1, 1, 3 minus the y hat vector, which we just found to be 1, 2, 2. And that's going to be the length of 0, negative 1, and 1. And if you do the square root of the components squared, you're going to get a length of square root of 2. So it is square root of 2 units away from the y vector. That length, that blue line, has a length of square root 2. Let's do one more example. Here we have u1 equals 2, 5, negative 1, u2 equals negative 2, 1, 1, y equals 1, 2, 3, and w, the surface that we're talking about, so I could kind of sketch out this surface again, is the span of u1 and u2. So u1 and u2 lie somewhere in here, and not only do they lie in there, but they need to be perpendicular so that we could apply this technique. So there's u1, u2. And those lie inside the plane. So let's just check their dot product. If I multiply, I get negative 4 plus 5 is positive 1 minus 1 is 0. Perfect. So they are orthogonal. That's exactly what I was looking for. Now I have some other vector in here that is off the plane. And what I want to do is I want to project that down onto the plane. So I want to basically find this vector, this blue vector, which is the y hat, such that whenever we project this down right here, this angle is going to be right. And this, of course, this green vector is my y vector. So we're going to go through the same process. The first thing I always like to do is just write out the equation. The y vector is c1 u1 plus c2 u2. Now, because it's not in the plane necessarily, I can't just say y is a linear combination of the two vectors in the plane, because then y would have to be a vector inside the plane. So to be able to represent any vector y in 3 dimensions, we would have to have a third component, which we're not going to find and we're not going to worry about. We really just need to establish the fact that this is our y hat vector and that this is the z vector. So to get y hat, we're going to calculate C1. So we know that C1 is going to equal y dotted with U1 over U1 dotted with U1. And that's going to come out to, let's see, so y is the vector 1, 2, 3. U1 is the vector 2, 5, negative 1, divided by 2, 5, negative 1, dotted with 2, 5, negative 1. So in the numerator, let's see, we'll get 2 plus 10 is 12, minus 3 is 9. And here we'll get 4 plus 25 is 29, plus 1 is 30. So C1 is 9/30. And C2 is going to be a similar computation, but it will be y dotted with U2 over U2 dotted with U2. And just to carry that out one more time, we'll have 1, 2, 3. The U2 vector is negative 2, 1, 1, divided by negative 2, 1, 1, dotted with negative 2, 1, 1. And let's see, that comes out to negative 2 plus 2 is 0, plus 3 is 3. Positive 4 plus 1 is 5, plus 1 is 6. So this comes out to 1/2. So we've just found that y hat, which is C1 U1 plus C2 U2, is going to be 9/30 times the 2, 5, negative 1 vector plus 1/2 times the negative 2, 1, 1 vector. And I could do the computation on that. And we get the vector negative 0.4, 2, and 0.2. So that is this blue vector here. We just found out that the shadow that's being cast down onto this plane is the vector negative 0.4, negative 0.4, 0.2, rather 2 and 0.2. And so that is the vector that we just found to be the orthogonal projection of y onto w. And the way we could write that is similar to the notation above. We say that y hat is the projection of y, but now it's not onto a vector, we're projecting it onto a plane, which we're just calling w. And that's it. We'll go ahead and stop there.